and welcome to this video on load balancing. Today we will talk about load balancing benefits and load balancing algorithms. Let's get started. Imagine you have a simple server and it's able to take one request at a time. Perhaps you have some new features and you are starting to get multiple requests in quick succession. This means these requests are lining up and each one has to wait for the preceding request to finish in order to be processed. You can expect to see the server overloaded and the response times to skyrocket, resulting in a lot of frustration by the user making the request. So an easy fix to this problem is to have multiple servers to spread the load. So with multiple servers, you need to figure out a way in which these servers would coordinate with each other. In a simple case, these servers have no way to communicate with each other. Enter a load balancer. This load balancer, which could be a server or some other kind of device, will spread the traffic across this cluster of servers to improve response times and the availability of the application, website, or database, whatever you got going on there. A load balancer will now keep track of all of the resources while distributing these requests. Maybe a server is not available to make a new request, or it isn't responding. Maybe it even has an error. Well, the load balancer will now stop sending the traffic to the server. As you can see in the diagram, the load balancer is now a centralized point that sits in between the client and the server instances. It accepts incoming network and application traffic and distributes the traffic among the multiple backend servers. By balancing application requests across multiple servers, a load balancer can reduce the load on an individual server and prevents one application server from becoming a single point of failure. So it provides two things to the application: availability and responsiveness. To utilize full scalability and redundancy, we can try to balance the load at three different layers within the system. This first place here, as you can see in this diagram, is between the user and the web server. The second place here is between the web servers and the platform layer. Let's say you had a website that serves some pages that require some real complex calculations for some requests. If both of these functions were on a web server, then a calculation would increase the response time of the web pages. So having it on a separate server avoids this problem. You can call this the platform layer, the application server, cache server, or business layer. It's pretty much where the business logic lives. And lastly, the load balancer can be placed between the internal platform layer and the database here. So what are the benefits of load balancing? Using a load balancer obviously increases user experience by making it faster and maintains uninterrupted service. A user won't have to sit around and wait for the server to finish a previous task before it processes their request. So what are the benefits of load balancing? Using a load balancer obviously increases user experience by making it faster, and it maintains uninterrupted service. A user won't have to sit around and wait for a server to finish a previous task before it processes their request. Service providers experience less downtime and higher throughput. Let's say a single server failed completely. The load balancer will simply route around this failed server and send it over to a healthy server so the user's experience is unaffected. There are smart load balancers too that can do cool things like predictive analysis for determining traffic bottlenecks before they occur. So a smart load balancer will provide an organization insights that are actionable and can optimize their business decisions. Lastly, system administrators experience fewer failed and stressed components. Instead of one single device doing all the work, load balancing has a bunch of different devices performing a smaller piece of the total amount of work that it must do. Now we have to talk about how the load balancer chooses the backend server. There are two different factors considered before forwarding a request to a backend server. And these two factors are health checks and the method used to configure the routing. They first ensure that the server they are sending the request to is actually responding appropriately to requests, and then use a pre-configured algorithm to select the healthy servers. Health checks are one way to define a healthy server. The health checks are regularly attempting to connect to the backend servers to ensure that the servers are listening. If a server fails a health check, is then automatically removed from the pool of healthy servers, and the traffic won't be forwarded, or at least until it responds to the health checks again. There are a variety of balancing methods which use different algorithms for different needs. So your load balancer may support multiple load balancing algorithms, and it might be hard to choose which one you require. We will get a better understanding of what each one does to support your choice. We'll take a look at 8 different methods to choose from. We have the round robin and the weighted round robin, the least connections, weighted least connections, least response time, least bandwidth and the least packets, and the IP hash. We're going to visualize the round robin and least connections, and then briefly introduce the last few. I think you'll get a good understanding once you see the first two in action, and it'll be easier to visualize how the remaining methods work. Round robin is the most popular load balancing algorithm. It is easy to implement and easy to understand. Let's say you had 2 servers waiting for requests behind your load balancer. Once the first request arrives, your load balancer will then send that request to the first server. Then when the second request arrives, let's say from another user, user 2 here, that request will be routed to the second server. Now, if the third request arrives, because the last request was routed to the second server, this third request will be routed back to the first server. The fourth requests are routed to the second, and this continues back and forth as the requests come in a cyclical fashion. A simple sort of implementation, but this will not perform that well in certain scenarios. For example, if server 1 had more CPU, RAM, and all the bells and whistles compared to server 2, server 1 would be able to handle the larger workload compared to server 2. The load balancer wouldn't be able to make this discernment and will continue to distribute the requests back and forth from server 1 and server 2. Server 2 can be overloaded much faster than server 1 and will eventually be worn out, and it will fail. That leads us to the weighted round robin. Now, the weighted round robin. This is similar to the round robin method. It's a cyclical method where the load balancer will alternate from one server to the other, but there is a twist. The server with the greater specs will be proportioned with the greater number of requests. And this is defined through the configuration of the load balancer, indicating which server has the higher specs, and basically it assigns a higher weight to the first server. So if server 1 had a capacity that was 5 times greater than server 2, you would assign a weight of 5 to server 1 and a weight of 1 to server 2. So when the requests start to come in, the first 10 requests the first 5 requests will be assigned to server 1. And then the 6th request will be routed to server 2. And the 12th request will also be routed to server 2. Capacity isn't the only reason for choosing the weighted round robin method. Sometimes if you wanted one server to get a smaller amount of requests, let's say to an equally capable server, and maybe that's just because of some complex calculations being made on one of the servers, and you don't want that server to be easily overloaded. Now let's look at least connections. Let's say that 2 servers in a system are equally comparable in capability. One server can still get overloaded considerably faster than another server due to the amount of time a user stays connected with that server. Now, this would cause the current connections to one server to pile up and eventually exhausting the resources of that server, while at the same time, the other server in the system isn't really taking on much of the workload. In a situation like this, the least connections method would be the best choice. This algorithm takes into consideration the number of current connections each server has. When a request is made, the server will identify which server has the least amount of connections routed to the server and assign it accordingly. Let's say we have 3 connections routed to server 2 and only 2 connections to server 1. The load balancer will recognize that server 1 has 2 connections and assign this new user now to server 1, the one with the least amount of connections. Now, there is a weighted least connections method, and this can be configured the same way our weighted round robin example was. In this example, server 1 has the greatest specs again, and will therefore route more traffic to server 1 to proportionally spread the workload between the two servers based on specs and the least amount of connections. The last 4 methods we will discuss on this slide, because I think you can catch the drift now, first one is least response time. In the least response time algorithm, the backend server with the least amount of active connections and the least average response time is selected. Using this algorithm ensures quick response time for users, because if the server did not have a large workload relative to its CPU, RAM, and other specs, the response time will be quicker. Then we have the least bandwidth method, which is very similar to the least packets method. In the least bandwidth method, backend servers are selected based on the server's bandwidth consumption, and it will select the server that is currently serving the least amount of traffic, which is measured in megabits per second. Similar to least bandwidth method is the least packets method. Here, the server transmitting the least amount of packets are selected by the load balancer. Now, the last method for today is IP hash. IP hash load balancing involves looking at each user's IP address and making a determination from there about which server will handle the connection most quickly. A hash of the IP address of the client is calculated to redirect the request to the server. Now, in a system design, the load balancer can be a single point of failure. To eliminate the single point of failure, a second load balancer can be connected to the first load balancer to form a cluster. Each one of the load balancers perform health checks on each of the servers, and both are equally capable of routing traffic and failure detection. So in the event that the main load balancer fails, the second load balancer assumes its position and takes over from there. So there's a quick refresher of load balancing, its benefits, and some algorithms that were associated with it. I hope you guys took something away from the video or were refreshed in something, and hope you have a good one. Thank you.